Hello and welcome to another live stream brought to you by Portland State University's Learning Center. My name is Travis. I am a physics tutor here, and we're going to be doing potential energy and potential voltage. Or a few things first off, I want to post a few links that I always post in there. We got links to our Learning Center there. There's also going to be some links to the Learning Center's Facebook and Instagram pages as well. So definitely check them out, follow them on Facebook, Instagram, and see what type of sources they have available for us. If you're here for a class, I have an attendance sheet, which is a Google form that you can fill out. I'm going to paste the link in the chat right there. So definitely fill those out. I'm going to paste the link to that at the end of the lecture as well. And we can now get started. So we're talking today about potential energy. And potential energy is, for electromagnetism, is very similar in a large way to like potential energy of gravity. The equations are a lot different, but it's the general idea that if you release a system that has potential energy, the potential energy will cause work to be done. So we can define potential energy as the work done to accelerate a positive charge from rest. And results in potential energy. We also see this as kind of a negative or a negative change in potential energy. So when two charged particles are really far away from each other, so the distance between them is approaching infinity, the work or the force between them is practically zero. So we say as the particles are infinitely apart, the potential energy is zero, and as they get closer together, the potential energy is one, or not one, but it's larger and larger, basically. And as far as whether or not things are positive or negative, we say that the electric potential energy is positive if both charges are the same sign. Both charges are the same sign. I'm going to emphasize positive and the same sign. So we know, based on the Coulomb forces, if there's two charges that have the same sign, the result is their force is going to be repelling, going away from each other. So whether they're both positive or both negative, they're both going to repel each other. And we say that's a positive potential energy because it's going to approach the distance between them is getting larger, so the distance will end up becoming an infinity. If the charges are opposite signs, we can say the electric potential is negative. If the charges are opposite signs. And that makes sense as well, because if the Coulomb force between them, if they have two different signs, they're going to be an attractive force. So they're going to get closer together. The distance isn't going to approach infinity ever. It's going to get closer and closer until they're eventually zero distance between them. So looking at the work done by those is basically, it's going to be a positive work, which gives us a negative change in potential energy. And as always, the conservation of mechanical energy is always a thing, because energy in any closed system has to be preserved. So we say that there's conservation of mechanical energy. Which comes down in this case to the kinetic energy plus the potential energy needs to stay constant. And that's going to be true with most systems that you see. The kinetic energy and the potential energy are always constant for any type of system. And there's lots of different types of potential energy. Here we're going to focus mainly on electrical potential energy and electrical potential voltage or voltage potential. So let's move on. 1 second. I'll be right back. All right, I'm back. Let's move on to this problem here. So it asks, will the electric field strength, being E, between two parallel plates exceed the breakdown strength for air, which is 3 times 10 to the 6th power in volts per meters, if the plates are separated by 2.4 millimeters and a potential difference of 4,600 volts is applied. And says determine this by calculating the electric field strength between the two parallel conducting plates. Well, one relationship that we have here is this electric field is going to be equal to the change in voltage over distance. Because voltage in this case is kind of the difference, like the potential for electricity to go through there. And we can calculate it based on that. So in this case, we can say that the electric field, using the values that they have up here, 46,000 volts, and the distance here, 2.4 millimeters, we can calculate that electric field simply by saying that it's 4,600 volts divided by, I'm going to change this to meters. And if we plug it into our calculator, a new one. That's 4,600 in volts divided by 0.0024 meters. It gives us a value of 1.917 times 10 to the 6 Newton Coulomb. That's 1.917 times 10 to the 6. I'm going to use the units here, voltage per meter. It's really the same. This is the same thing as newtons per coulomb. It's just since we're dealing with voltage here, we're going to deal with that. So that's going to be the electric field in this case between those plates. The question then becomes the breakdown strength. So it is for the breakdown strength of air. Is there enough voltage potential to cause the breakdown strength to surpass that breakdown strength? We can see that 1.917 times 10 to the 6th power is a smaller value than 3 times 10 to the 6th power. So in this case, there's not enough voltage there to surpass that breakdown strength. So the question then is, how close do they have to be? How much of voltage do we have to apply before that air breaks? And to determine that, we use that same formula, which is the electric field potential or magnitude is equal to the change in voltage over distance, and we just rearrange it for the distance between them. So by rearranging that, we have a distance equal to that voltage over the electric field. I'm looking at our values again. 4600 volts divided by 3 times 10 to the 6 volts per meter. We end up getting, back to our calculator, 460 divided by 3 times 10 to the 6, given in our units of volt per meter. We get 0.00153 meters. That's 0.00153 meters, which is about 1.53 millimeters. So that's the distance plates have to be from each other to get enough, strong enough electric field to have that air break like that. So now we look at this problem here. This one's saying that there's a particle with charge Q1 was equal to 4.9 microcoulombs, and it's located at the origin. A second particle with charge Q2 is equal to negative 8.6 microcoulombs is located at, well, x equals 0 and y equals 4 centimeters. And a third charge, Q equals 3, is equal to 4.8 microcoulombs located at x equals 3 centimeters, y equals 0. So they want us to draw out this diagram in the 3-charge system and show kind of the location of those. So if I were to draw this out, first I'm going to do my axes. And since everything's in basically on the axes or in Q, just on the axes, I'm just going to draw Q1. And we're going to say there's one charge here. This is Q1. And we said that's equal to 4.9 microcoulombs. So I'm going to write it as 10 to the negative 6 coulombs. Somewhere, I'm going to go about 4. So that's 1, 2, 3, 4. About right there is going to be our Q2, which is equal to negative 8.6 times 10 to negative 6 coulombs. And looking at Q3, be about right there. And that's going to be equal to 4.8 times 10 to the negative 6 coulombs. So we could draw lines between these now, kind of connecting up our system. So we want to calculate the potential energy of this 3-charge system. So in this, we have basically three distances, R1 to 2, R3 to 2, down here it's R1 to 3. And we're going to calculate the potential energy for all of those. And we can use the formula that the potential energy is equal to K Q1, or say QA QB, over the distance AB. So using the value we have here, we know that the distance here is equal to 4 centimeters. The distance here is equal to 3 centimeters. And the distance here is equal to the square root of 4 centimeters plus, or squared, plus 3 centimeters squared. And then we can use the values we have here to calculate out the total potential energy by adding up all 3 of those values. I'll be right back. Give the problem a thought a little bit. I'll leave this up here. I just need to check on something. Sorry about that. I had a nephew screaming bloody murder, and I wanted to make sure everyone was okay. But everyone is, so we'll continue. So we're trying to find the potential energy of this three-charge system. And we know we can do this by adding up the potential energy of each of those charges individually and finding that sum total of them. So the potential energy between 1 and 2, charge 1 and charge 2, is going to equal K, which is 8.99 times 10 to the 9th power, in the units of newtons, meters squared, over coulomb squared. That's going to be times the charges of both of them, so that's 4.9 times 10 to the negative 6 coulombs, times negative 8.6 times 10 to the negative 6 coulombs. And we're going to divide that by the distance between them. In this case, 4 centimeters. I put that in meters. Oh, I wrote millimeters. Let's fix that. I'm writing centimeters down. Meters, there you go. So we can do something similar. We can calculate that one first. So that's 8.99 times 10 to the 9th power in newtons, meters squared per coulomb squared. And that, of course, all the wrong thing. That's better. So that the whole value, that's K, times 4.9 times 10 to the negative 6, 4.9 times 10 to the negative 6 coulombs, times a negative 8.6 times 10 to the negative 6 power of coulombs. And we're going to divide that whole value by 0.04 meters. And that gives us a potential energy of negative 9.47 times 10 to the 22nd joules. Oh, wait, that does seem right. Seems like a really big number, and it's because I have a 16 instead of a negative 6 there. That looks a lot better. Negative 9.47 joules. So this is a negative 9.47 joules. And let's look at the potential energy between 1 and 3. Be the same idea, 8.99 times 10 to the 9th power Newton meters squared divided by coulomb squared times Q1 is the same, 4.9 times 10 to the negative 6 coulombs. Q2 in this case, Q3 is 4.8 times 10 to the negative 6 coulombs. We're going to divide that whole thing by the distance between those, which is 0.03 meters, 3 centimeters. Plugging that in, we can use the same equation we had before and just change the value here from 8.6, negative 8.6 to 4.8. And the distance on the bottom to 3 centimeters. And that gives us 7.05 joules. So that's 7.05 joules. And notice that the potential energy for Q1, Q2 is a negative value because both of them are opposite charges, basically. Right? So the attraction force is going to be a negative potential energy. But since Q1 and Q3 are both positive charges, it's going to have that repulsion force, giving it a positive potential energy. Now we just have to find the potential energy between Q3 and Q2. PE of 2 to 3 is going to equal 8.99 times 10 to the 9th Newton meter squared per coulomb squared times 4.8 times 10 to the negative 6 coulombs. And we're going to multiply that by a negative 8.6 times 10 to the negative 6 coulombs. and we're going to divide that. Here, we have to use that square root because it's the distance between them. And since it's at an angle, we can use the Pythagorean theorem to figure that out. So we can say that's the square root of, and I'll write 0.04 meters squared plus 0.03 meters squared. Plug in that bad boy into our calculator. So we still have that 4.8 on the top. Now we have a negative 8.6 as well, and on the bottom we'll just get rid of that and put a square root sign of 0.04 meters squared plus 0.03 meters squared, and we're at negative 7.42 joules. And that makes sense too, because they're going to be pulling towards each other there. So it's equal to a negative 7. What did I say? 7.4 joules. Let me look at that. Make sure I got everything right. 4.8 negative 8.6 8.99 coulombs. Yeah, that looks right. 46 joules. Now we should be able to add up all of these and get the value of everything. So if we sum up those three values, we should get the right potential energy for everything. So doing that, we have this value plus this value plus that value. The total sum is negative 8.45 joules. So the total potential energy, so let's say PE total, should equal a negative 9.845 joules. That's just the summation of the potential energy between each of the individual particles. There. Let's do something similar, but a little bit different to this one. Instead of finding the potential energy, we're going to look for the work it takes to move these four particles into position. So we can start with just particle 1. I'm going to call this down here particle 1, then 2, 3, and 4. So we know that the total work is going to equal the work to put the first particle in position plus the work to put the second particle plus the work to put the third plus the work to put the fourth particle there. And we can start it one at a time. So the first particle, to put the work there, we're moving a positively charged particle into position with nothing else around it. So assuming all these other ones aren't here yet, we're just focusing on putting that one there. The work to put that there, work of 1, is equal to 0, because there's no force between it and any other charge at that point. So that was easy. We can look at the second particle. This time we have some work to deal with. So the work of the second particle is going to be equal to K QQ over R1, 2, which is equal to 9.0 times 10 to the 9th power newtons meters squared over coulombs squared. I just rounded out my 8.9. That's my value for K. Multiply that times 2 times 10 to the negative 6 coulomb. That's the charge of that first particle. Times 3 times 10 to the negative 6 coulombs. And the charge of that second particle. And we can divide that whole thing by the distance between them. In this case is 0.01. Yeah, 0.1 centimeter or meters. Doing that, so I'm going to go, let's do 8.99 times 10 to the 9th in Newton meters squared, coulomb squared. We're going to multiply that by, I said 2 microcoulombs. 2 times 10 to the negative 6 coulombs times another 3 10 to the negative 6 coulombs. And we're going to divide that whole value by 0.01 meters. We get 5.34, or say 5.4 meters, or joules. 5.4 joules. And that's just the work it takes to put that second particle there with just the first particle nearby. Looking at the third particle, which is 4 microcoulomb up there. That's the third particle. This one gets a little bit more tricky because now to move that particle in, there's going to be work done from the first particle because there's a force between the first particle, and there's also a force between that second particle as well. So we have to move this into position with the force of both of those. So we have to account for the work from both those particles. We can say the work for 3 is equal to K Q1 Q3 over R13 plus K Q2 Q3 over R23. Summing that up, that's going to equal 8.99 times 10 to the negative 6. I'm just going to factor out that K value. We're going to multiply 2 times 10 to the negative 6 coulombs by, that was a 4 microcoulomb charge. 4 times 10 to negative 6 coulombs. Divide that value by the distance between those. Between 1 and 3, again, we have kind of that hypotenuse across there. This is a 1 centimeter cube. So luckily, this is the square root of 0.01 squared plus 0.01 squared. So I can just write that down here, 0.01 squared plus 0.01 squared. And we're going to add to that, go a little bit below here, so I have space. The force between, or the work between those two guys, 2 and 3. So that's going to be 3 times 10 to the negative 6 coulombs times 4 times 10 to the negative 6 coulombs. I see, divided by the distance there, which is just 1 centimeter. This is in meters. So that's what we need to add together to find that work to bring that third particle into position. Swing back to our calculator. I'm going to grab this top one here because this is very similar to the work that we had for 3, the one we had for 1. The 3 can stay the same. This one changes to a 4, and the distance between 3 and 4 is still 1 centimeter. So put a parenthesis here on that one. I'm going to copy my K value. Paste. That's why I love computers. Copy and paste is the best thing in the world. Now, finding the values for the charges 1 and 2, it's that 2 times 10 to the negative 6 coulombs times, in this case, it was 4 times 10 to negative 6. Coulombs. And we're going to divide that by the square root of 0.01 squared plus 0.01 squared in meters. I'm going to add those values together. And that is 15.9 joules. So quite a bit more work to bring that third particle in. I'm going to put it up here. This is 15.9 joules. And that's coming from up there. That's the sum of the work it takes from particle 1 and particle 2 combined. So now we need to find the work of particle, the work on particle 3 or 4. In this case, it's similar. We just add up another charge that we have to worry about over R13 plus K cubed. That's a G. Q should look like G's. 2. Or in this case, I should say 1, 4. A big eraser. 1 R1 4 4 R2 4 from R2 to 4 plus K Q 3 to 4 over R3 to 4. There we go. So adding up these values, I'm going to factor out that K out in the front. 8.9 times 10 to the negative 6 Newton meter squared over Coulomb squared. And I'm gonna add up then all of the charges. Q1 is 2 times 10 to the negative 6 coulombs. Multiply that by Q4. So Q4 was 5 microcoulombs. 5 times 10 to the negative 6 coulombs. Divide it by the distance between those, which is 1 centimeter as well, plus charge 2, which was 3 times 10 to the negative 6 coulombs, times charge 4, which is 5 times 10 to the negative 6 coulombs. Divide that by the square root of 0.01 squared plus 0.01 squared in meters. I'm going to add to that, in this case, charge 3 and 4, which is 4 times 10 to the negative 6 coulombs. I'm running out of space again. Let's adjust slightly. I just got to squeeze in a 5 times 10 to negative 6 coulomb there, dividing by 0.01 meters. I can close my bracket, and that should give us the total work done on the fourth particle as we move it in. So, if I say now 8.99 times 10 to the 9th power in Newton meter squared per coulomb, we're going to multiply that whole thing by B charge 1, 2 times 10 to the negative 6 coulomb times charge 2, or charge 4, 5 times 10 to the negative 6 coulomb. I'm going to divide that by the distance between them, which is 0.01 meters. We're going to add to that here. This is charge 2 now, which is 3 times 10 to the negative 6 coulomb. I'm going to multiply that by 5 times 10 to the negative 6 coulomb. I'm going to divide that by the square root of 0.01 squared plus 0.01 squared, and that whole thing should be in meters. We should then add the work done by third on the fourth, which is going to be 4 times 10 to the negative 6. 5 times 10 to the negative 6. We'll divide that by the distance between them, which is 1 centimeter. And I'm going to double check, make sure I have everything right. Got my K up in front. I can distribute all that in to get my works. And it looks like I got everything just right. Let's see. I missed something. Where did I miss? Coulomb. I forgot to square this guy. I knew it because my units didn't work out. The value should be right. There you go. 36.5 joules. So this is equal to 36.5 joules. In this case, all of the particles are positive, so the potential energy for all of them is going to be positive if we were to add those potentials. But in this case, we can add up all 4 of those values. The work for the first, so I can say work of 1 plus work of 2 plus work of 3 plus work of 4 is equal to 0 plus 5.4 joules plus 15.9 joules plus 36.5 joules. And adding up all those values, let's do it a little bit backwards. Got my plus in between here. There, I can just say plus 0 joules. It's 57.77 or 57.8 joules. It's the total energy, the total work that's being done here is 57.8 joules to move all those charges into position, that square configuration. So next we're going to talk a little bit about electric potential voltage. Just real quick, I'm going to run through here. We can say that the potential voltage is equal to the volts of B minus the volts of A, which is equal to the change in potential energy over Q. You can also think of it as the change in potential energy is equal to Q delta V. If you were to have a point charge on something, you can calculate its voltage equal to K times Q over R. R is the distance between them. The units for voltage is equal to joules per coulomb. So it's the energy per coulomb is there. We can also calculate work. Work is the negative work from A to B divided by, we can calculate the voltage using work. So the work from A to B divided by a charge is equal to that change in voltage from A to B. Similarly, just moving things around, calculating that work is equal to negative Q. We can just say VAB, which is the same as delta VAB. Those two are the same idea. It's the voltage between those 2 points. And we can use these ideas. So if we had a uniform electric field with kind of a hole in the middle of it. Say I had an electric field, going the wrong way, uniformly between some parallel plates. I could use that to accelerate an electron going out that way, because the voltage potential between those two plates will turn into an electric field, which will act on a force on that negative charge, accelerating that charge towards the positive sided plate, turning potential energy into kinetic energy. And we're going to explore that in these problems here. I think I probably have time for one of them. Lost a little time today. So this one's actually pretty cool. So hopefully we can get on to the second one. If the potential due to a point charge is 504 or 540 volts at a distance of 11 meters, what are the sign and magnitude of the charge? So if the volts is equal to 540 volts and we have a distance of 11 meters, we can use that equation we just said, V is equal to K Q over R. We rearrange it because we want to find the magnitude of the charge. So rearranging this, you get VR over K is equal to Q. So just plugging in the values into our calculator, we would say 540 volts times, that was divided by, times 11 meters, which is our distance between, or the distance they gave us for the point charge, divided by 8.99 times 10 to the 9th. Newtons meters squared per coulomb. Squared is equal to 6.61 times 10 to the negative 7 coulomb. That's 6.61 times 10 to the negative 7 coulomb. So that's an application of using a point charge to find the voltage at a certain point, or using that voltage at a point charge to find the charge itself. So if you detect the voltage, you can then back calculate to find Q, the charge. Let's go on this one. This is a bit more fun because we're accelerating electrons. An electron is accelerated in a uniform electric field having the strength of 2.3 times 10 to the 6th volts per meter. What is the energy in keV? Oh, yeah, given to the electron if it's accelerated through 0.3 meters. So we can break this one down as in the kinetic energy is going to equal the negative of the potential energy. Because if we start at rest, potential energy will turn into kinetic energy through the conservation of mechanical energy. So using this analogy here, or equation, we can then say the change of potential energy is equal to negative QV. So the change in kinetic energy is equal to Q delta V. And we can look at delta V as being the same as the electric field times the distance. So now we've broken it down. So the change in kinetic energy is equal to QED. And that will give us, using that formula, we can use this to now determine what's going on here. So just like I drew before, we have this voltage potential going, an electric field going between two parallel plates, and we want to accelerate an electron through here. Yoink. So accelerating this electron flying out this way based on the electric field going through the magnitude of the electric field. And we know the charge, Q, is equal to the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. You know the electric field is equal to 2.3 times 10 to the 6 volts per meter. And we know that the distance is equal to 0.3 meters. So we say that the kinetic energy of that would equal 1.6 times 10 to the negative 19 coulombs times the 2.3 times 10 to the 6 V over M times 0.3 meters. Calculate that very quick. Wrong one. That's the one. So that's, I'm just going to use Q, because Q gives me my charge of the electron. So that's Q times the 2.3 times 10 to the 6 volts per meter, without my underscore, times 0.3 meters. That's 1.15 joules. Something is wrong. Q 10 to the 6 volts per meter. That's what's wrong, is I need to convert it to electron volts. So remember, there is 1.6 joules per electron volt, so we can literally divide this whole thing divided by 1.6 times 10 to the negative 19. I'll put it in joules. And that should be how many electron volts we have, which is about 690 kilo electron volts. So 690,000. Go away. There it is. And that is the energy that's given to the electron just by being in that electric field. That's about all the time we have for today. Definitely make an appointment with the tutor up above me if you're watching in the Pinch app, or drop into my drop-in hours, which is directly following this from 2 o'clock to 3 o'clock. Thank you all for joining, and have a great day.